So this is 6.1, estimating with finite sums. And this is unit 6, the definite integral. So a nice quote from Albert Einstein. God does not care about our mathematical difficulties. He integrates empirically. I actually use that a lot when I do this. So yeah, we'll see. By the end of this chapter, you should be able to approximate the area under a curve with multiple methods. It's pretty straightforward. Understand what Riemann sums are. They're actually kind of tricky, but very doable. I don't think you have any major problems with that. Understand what a definite integral is, how it relates to area, and then go back and forth with fundamental theorem of calculus, where we connect differential and integral calculus. And then how do you actually do it if you're not estimating? Well, you use antiderivatives to calculate these, which is not too bad. And then you could also estimate with a trapezoidal rule. I don't know why we don't put that earlier on, but we don't. So let's go. Just so we're clear, this is the start of integral calculus. And integral calculus is the inverse of, I don't know if it's correct to say inverse. It's the opposite operation would be a better way to put it, of differential calculus. So we're going to combine the two eventually, but let's just take a look at how the integral is going to work. And it's basically area under curve. So if you took nothing else away from this lecture and just said the integral means area under a curve, then you are way ahead of the game. And many of my students are starting to figure out the answer to a lot of my questions is just graph it. Shout out to Hogue for that one. And if you get stuck in a problem, we'll just graph it. You're probably gonna have to graph it by hand, but it's not a big deal. Just what's the area? If it's a easy geometric shape, off you go. So for example, train travels 7 to 9 at a constant rate. How far has it gone? Well, hey, we could do that with distance equals rate times time. And that is 75 miles per hour times 2 hours, 150 miles. Piece of cake. Well, let's show how we would do it with calculus. And we want distance from velocity, so we would integrate, which is the opposite of differentiation. When we went from s prime of s of t to s prime of t, which is the derivative, we use a derivative. To go backwards, we use an integral. I'll show you briefly how that's going to work right now. Hey, we're going at 75 miles per hour from 7 to 9. Sorry for moving the page on you. I'll bring it back as soon as I can. So what's the area of this box? That's it. It's the same thing, right? Formulas derived from calculus, but you don't know that. You just think they're these magical formulas that somebody knows. And then the calculus. So what if the train is accelerating and decelerating all the time? How would you find the distance traveled? What if we had this situation? From 7 to 9. So what if, sorry, get interrupted there, if it was bouncing around? How do you find that area? Well, integral calculus can do it for you exactly, but we can approximate things, which is pretty slick. So for example, particle starts and moves along the x velocity with a velocity, x-axis with a velocity, and it's just t squared. So how far has it traveled? There. Well, we can just approximate. And we can say, like, let's go to the midpoint. So let's go to 0.5 and then 1.5 and go up till we hit. You might be like, well, why don't you just ballpark it, make triangles and stuff? Yeah, we will. But we have to come up with like kind of an automated system where we're all on the same page. You see this gap here should fill in this gap a little bit, but not very well. It looks like this will be something of an underestimate, but it'll get us close. If that's what we're trying to do, is get close, and we're fine. So the height is 0.5 squared, and the width of the rectangle there is 1 plus 1.5 squared, because 1.5 squared is the formula, times 1 plus 2.5 squared is 1. It's 8.75. Now I said underestimate. I think I was guessing and I got lucky. No units here. It's actually 9. So we did pretty good with just kind of a ballpark estimate. How do I know it's 9? Because we're going to do the opposite of the derivative. We're going to add 1 and divide by that. That's 2 to the third over 3. And then we're going to plug in 3 and 0 and subtract them. It'll be 27 over 3 is 9 minus 0 is 9. What just happened? Yeah, I know. We got to get there. One small baby step at a time. All right, so we just did a midpoint rectangular approximation. Slick. Yes, I know. I think it's slick too. Are there other methods? Yeah, there's plenty of other methods. So let's take a look at what we could have done there. We could have done what we call, that was MRAM. We could have done what we call LRAM. Where we go up to the left and come across. Well, there's nothing in there. And you go up to the left, come across. There's nothing in there. Go up to the left, come across. And you might be like, well, dude, that sucks. It's not nearly a good enough estimate. And I would say, you're right. But we use calculus, make these gaps smaller and smaller and smaller. Our approximation is going to get better and better and better. So we can start with this and just make a limit. It's going to work. We also do RRAM. Which point you'll say, dude, that sucks. There's just these huge extra chunks. That's way too big. And I would say, you're right. But we could use calculus, make a limit, get closer and closer and closer. So let's try an actual example. Find the area under the curve, x squared sine of x. I happen to know that it graphs something like this. Plug in 0, we get 0. Plug in pi, we get 0. And we're out here at 3.14-ish. So we'll just do it from 0 to 0. So we're going to be a little bit above. It's going to look something like that. Is that 3? So hey, let's break it in chunks. And let me go back here. What information do I need to give you in order to perform this method? Well, I have to tell you type. And that means LRMRAM. And interval. And you can't do it otherwise because you could put a zillion intervals in. All right, so here I didn't say anything. Let's assume I said 3 intervals. So we're going to go with MRAMs. So we go to 0.5, 1.5, 2.5. We bounce up here and we make our square. We bounce up here and we make our square. We bounce up here, we make our rectangle. I've been saying square, that's a rectangle. You say, what are the areas of all these squares? Hopefully that's about right. And it's at 0.5, 0.5 times sine of 0.5. That's the height times the width, 1, plus 1.5 sine of 1.5, make sure our calculator's in radians, plus 2.5 sine of 2.5 times 1. Put it together and we get a number. Let's see what we get, and then I'll show you how to cheat on your calculator, a scheme on your calculator. So, oh, I forgot to share. Hold it. Always forget I'm in Zoom. Share screen, calculator, woohoo. Go away. All of them being multiplied by 1, so I'm not going to bother with that. 0.5, just I gotta check. Radians. 0.5 times sine of 0.5 plus 1.5 5 times sine of 1.5 plus 2.5 times sine of 2.5. We get 3.232. I'm going to write that down on the page over here. We'll bounce back and forth real quick. So 3.232, no units. Now, here's how we draw it. The integral from 0 to 3, this just means find the area under the curve of x squared sine of x. And just like with derivatives, we have to say with respect to x, that means with respect to x equals. Now you can do this on your calculator, which is the main reason you won't be allowed to use it at the end of the unit when we take the test. And it's in the same exact spot as your numerical derivative, number 9. And look at that, it popped up the same way. The integral, meaning the area under the curve from 0 to 3, x squared times sine of x with respect to x, 5.777. So our estimate is way off, which doesn't make any sense. I don't see what we did wrong there. Yeah, I forgot all the squares, didn't I? I forgot it was x squared. So nice, let's go fix it. It's nice that I actually figured it out this time. So 2.5, second insert squared. Nice. 0.5 all the way over here. Second insert squared. And then second insert squared, enter. 6.104, so let's go fix that. And then 5.777, 6.104, 5.777. This actually is correct, but it's supposed to be squared, squared, squared. 5 point, I'm changing the screen, you won't see it. 777. And then over here, 6.104. .104. You'll find this very accurate because it does the same thing with more divisions. It's a numerical integral. So this is just your introduction. Things are going to get goofy very, very quickly. You might want to lock this down now. Good luck and happy mathing.